Hello everyone. Today I'm going to talk about Alberta surface water resource challenges and management. So the first thing I will talk about is water supply and demand in Alberta. Next, I'll try to give you some example of challenges that we face in water supply and demand. I also want to talk about water management. And finally, I'll give you some examples of projects. So let's move into the first portion of my presentation, which is surface water supply and demand. In this slide, you can see there's a map on the right side, and it's sort of a hydrologic cycle in a provincial scale. In Alberta, on an average, 500 millimeter of precipitation falls in a year, and because of the semi-arid climate, 3/4 of that amount actually get lost in terms of evapotranspiration. And then we have groundwater reachers which go deeper into the aquifer, about 40 millimeter, and surface runoff is about 100 millimeter, which is 1/5 of the precipitation. Let's talk about continental river basin in Alberta. We have 3 continental river basin. So the first one is north flowing Mackenzie River Basin, which actually drains into Arctic Ocean. The next one is east flowing Nelson Churchill River System, which drains into Hudson Bay. And then we have Mississippi System that drains into Gulf of Mexico. These are the 7 major river basins in Alberta. These are Water Survey of Canada's sub-watershed. Now, let me give you an example of how this continental, subcontinental, and other river basins are connected. So, this is a station identification number for North Saskatchewan River at Edmonton. The number is 05DF001. So the first 2 digits, 05, it's actually coming from the subcontinental river Nelson river system. D is coming from North Saskatchewan River, so it's a code of North Saskatchewan River under Nelson river system. F is coming from a sub-watershed within the North Saskatchewan River watershed, which is from Strawberry Creek to Edmonton Low Level Bridge. And then the next 3 digits is just a station identification number. Now let's talk about water supply. The right hand side of the slide, I have a map of Alberta with all of the major rivers, and what we are showing here is a sort of buffer zone around all the rivers, and these buffers are based on mean annual flow of that particular river. Now, the takeaway from this slide is all the northern rivers, they have more flow compared to the southern river. So that implies we have more water supply in the north and we have less water supply in the south. Now, these are the summary of information that I already provided. So Alberta is relatively dry weather because of its semi-arid climate. It has only 2% of Canada's water resources, and water supply is not always balanced with the distribution of population. And as you can see, 87% of the water is basically in the north flowing Mackenzie River system that drains into Arctic Ocean. 13% of the flow is going to east flowing Nelson system that drains into the Hudson Bay, and only a fraction of the water is actually going to Mississippi system and drains into the Gulf of Mexico. Now, I also want to talk about water demand, and before moving into that discussion, I wanted to let you know 2 different things. One is allocation and one is water use. Now, all water in the province is the property of Crown. That means if someone needs to withdraw water for development for other purpose, they actually need to apply for a license. Now, there are some exception for that. So there are some water use are exempted under the Water Act, but in general, if you wanted to withdraw water from a river or from a lake, you actually need to apply for a license. Now, when someone applies for a license, they actually have to provide some sort of information on how much water they need in an annual basis. Now, we call that allocation. So this is the theoretical maximum water that can be withdrawn for that purpose. However, the reality is actual water use is much less than water allocation. So because we cannot track all the actual water use, we do have all the tracking system for water allocation because they are theoretical number. So just to be mindful that water allocation is not always water use. And often we actually use water allocation as a proxy of water demand. Now, this pie chart we're showing how much water is being allocated until 2017. You can see that most of the water allocation is from the surface water, which is about 97%, and only 3.4% is groundwater. Again, in this pie chart, we are showing the total water allocation by 2017, but now we group them into different types of water use, like agriculture or irrigation or commercial. In this slide, we are showing the total allocation in Alberta by river basin. As you can see, the South Saskatchewan River Basin has a lot of water allocation compared to northern rivers like Hay. Now, in this plot, I'm showing the total water allocation from 1900. So it's just a way to show that how water allocation is increasing over time. Now let's move into some of the surface water challenges. So the first one I want to talk about is water supply and demand imbalance. So in this slide you can see two different maps. The left one is showing that how water is distributed all over the province. We have more water in the north compared to south. The right side is showing that how different river basins, how much water is already been allocated from that river basin. Now, if you look at these numbers, so if you move more south, you'd see that more water is being allocated from that portion of the province compared to the northern Alberta. So now, when you look these two plots side by side, you would notice that we have more water on the north and less in the south, but water demand is more in the south and less in the north. So it's a complete imbalance between water supply and water demand. The next challenge is inter-annual variability in water supply. So you can see a hydrograph of Athabasca River below Fort McMurray. We have data from 1957 until 2011. And what we're showing in this plot is in y-axis we have stream flow, in x-axis we have dates, like from January to December. Now we have two different bands here. So the light blue band is showing you the natural variability in terms of minimum flow and maximum flow. And then the dark blue shaded area is showing you, we call it normal flow. And this is basically a range between the lower quartile and upper quartile. So if you have 25% exceedance probability and 75% exceedance probability, basically this band is showing in between those ranges. And the black line is showing you the 50 percentile exceedance, which is the median flow. Now the reason I'm showing this plot is just to demonstrate that how uncertain our flow could be, especially in our rivers. So this is the natural variability of stream flow in a river. Now then we do have systems where water flow is being regulated by dams or reservoirs or even water withdrawal. So in the left side of the slide you can see major dams or minor dams and their locations. So you can see that in the southern Alberta, a lot of rivers are actually regulated. So, and what it exactly mean by that, I can show you in this plot. So again, the blue shaded area is showing, the regulated normal range. Again, this is in between 25th and 75th percentile. However, this, lines like This gray lines is showing, what would have been the natural variability if the river wasn't regulated. So basically, this was the river before we started the regulation, and this is the river right now after the regulation, and this is for the North Saskatchewan River. So this again tells you that, a lot of times our river are regulated, so their hydrology has been changed. So we have to also keep that in mind when we talk about water management. Now, the next thing that I want to talk about is, hydrometric stations. So I have different maps. So the left side of the map, I'm showing you, all the Water Survey of Canada stations in Alberta. All these dots are one of the hydrometric stations. However, not all the stations are active all the time. So right now we have only about 450 active stations, which is 42% of the total station. Now, when we move to this maps, things becomes even more complicated. Now, only 32% of those stations actually have more than 30 years of data. Now, if you look at how many stations we have more than 50 years of data, it's about 12%. And only 1% of the station we have more than 100 years of information. And then we have transboundary agreements between other provinces. So we have the 1909 Boundary Water Treaty with the US, and that's for the St. Mary and Milk River. We have 1969 Master Agreement on Apportionment. That's mostly for the east flowing rivers. And then we have 1997 Mackenzie River Basin Transboundary Water Master Agreement. Now, next thing is the climate variability. So Alberta has some impact from El Nino Southern Oscillation. You probably heard about it. Every 5 to 7 years, there is a warming and drying episode, and also cooling and wetting episode. So we call them El Nino and La Nina. Now, this is just to give you an example that how El Nino and La Nina can affect our stream flow. So this is Bow River at Calgary. So these are like, mean annual flow, you can see. And then what I did, I find out which years are El Nino years and which years are La Nina years. Now, this dotted blue line is showing, the average stream flow in La Nina years, and then dotted red lines is showing average stream flow for El Nino years. So, and the black line is mean stream flow for the total time period. So you can see that in an El Nino years, usually the stream flow is less than what it should be, and you could see the opposite effect in the La Nina years. And the next thing, we called it Pacific Decadal Oscillation. So again, it's a sort of similar oscillation like ENSO, but it happens every 20 to 30 years. So it's a longer phase period. And I did the similar plot for the same river. Again, we have mean annual flows for Bow River at Calgary. And then what I find out those warm and cold episode of PDO. And you could see that when there is a phase like positive phase and negative phase, right? So you could see that the stream flow could be quite different than the mean annual stream flow. And then we have climate change impact on water resource. So this plot, I have taken it from one of the report published by Environment and Climate Change Canada. It's showing how stream flow is being changed in the historical time period. You could see there's a lot of negative numbers. Negative means significant decrease. So the and then positive means increase. So these are basically the historical trends, and also there are some projected numbers as well. So you could see there's a lot of negative projected numbers in Alberta as well. This is a photograph I've taken from this this paper. It's showing that how things were in 1898 and how things are in 2003. I can see there's a lot of glacier retreat there. This is a similar kind of photograph, and things have been changed from 1897 to 2002. So again, whatever I have discussed before, this is just a listing of things that we faced in terms of water supply challenges. So definitely, water supply is not balanced with the distribution of population. We do have year-to-year variation of stream flow, and then a lot of our rivers are regulated, so we do have that stream flow changes in natural versus regulated rivers. Also, we don't have sufficient long-term monitoring station, like stations more than 100 years of data, and also there are changes in water supply happens all the time in terms of climate variability, like the ENSO and PDO, and also probably in terms of climate change as well. We do have water demand issue. Again, water demand is not balanced with the distribution of water supply. Our demand are also increasing. We do have transboundary apportionment agreement, and we have to meet apportionment amount, so let others also use the water. And also the water demand can also be changed under the impact of climate change and also climate variability, like ENSO and PDO. Okay, so let's move into some of the water management issues here, or information. So I want to give you some example or some information about the legal basis for water management in Alberta. So it started with the Northwest Irrigation Act in 1894, and around that time the federal crown, the Dominion of Canada, actually declared the ownership of water, and then started providing license for water use and also prior allocation system, which is sort of first come first serve. In 1930, the federal government actually transferred the natural resource to the provincial crown, and then in 1931 we have the Water Resources Act, and which is similar to Northwest Irrigation Act. Again, we have to apply for license for water use, and also it's first come first serve. And then in 1999 we have the Water Act, again, which is revised for licensing approval process, and it also has public consultation, but again, the first in time priority, it was maintained. So whoever applied first, he has the priority for that water use. It also enables water management plan, which I'm going into a little bit details after this slide. It also allows license transfer. So important information is, under the Water Act, all the water resource in Alberta is the property of Crown. So if you wanted to use water, you need to apply for a license. In 2003, the Alberta government actually published the Water for Life strategy. It also renewed in 2008. Now, as I mentioned in the Water Act, so we do have water management plans in the province, and these are basically the approved options and a strategy for the management of various river basins in Alberta. And these plans actually recommend a sort of a social, economic, and environmental balance between water use, and so that we allow water use for economic development. At the same time, we also have to protect the environment. Now, these are the approved water management plan, and anytime you can go to Alberta Environment and Parks website, you could see these listings of water management plan. And I want to talk a little bit about that South Saskatchewan River Basin water management plan just in a moment. The South Saskatchewan River Basin, it has 4 sub-basins, Red Deer, Bow, Oldman, and South Saskatchewan. You can see in the map a sort of color code for different sub-basins. And what important for that water management plan, that when it was first approved in 2006, it basically established a limit on water allocation for the Bow, Oldman, and South Saskatchewan River Basin. Now, what it meant at the time, that because those 3 river sub-basins were over allocated at the time, so basically it put a limit, and it established water conservation objectives for those sub-basins, and also for the Red Deer River sub-basins. And then in 2007, the Bow, Oldman, and South Saskatchewan River Basin allocation order was passed, and what happened at the time is basically, we the government reserved those 3 subbasins, for so that no new license is allocated for those 3 subbasins, except for some uses like First Nation use, water conservation objectives and storage of water, and existing water license applications for any purpose on on the file when the order was passed. Now, a lot of work's background of the South Saskatchewan Water Management Plan was using water management model. So we call it WRM-DSS. So it's a priority-driven optimization model, and it was developed by Alberta Environment and Parks and being used since early 1880s. So what it has, it uses linear programming techniques to optimize the supply and demand. So I can explain things a little bit in the next slide. So for example, this is basically a schematic of South Saskatchewan River Basin Water Management Plan, the model network. So you can see this is the radier system, we have the bow system, and then we have the Ullmann system over here. And just to zoom a small portion of that thing, so you can see, these are like natural river network, and then we have different types of water use like irrigation, non-irrigation, and every water user, they have an identification number, and then what the model try to do is the model try to balance between the supply and demand. So there is a constraint has been set, and which is based on the priority number of the license. So license that have highest priority, the model try to provide water for those license compared to the license which have lower priority than the first one. Now, I want to give you 3 different examples. First one is water availability in Alberta lakes. So this is a new directive that approved by the department in 2019. It's a surface water allocation directive. So this directive gives direction on how water will be allocated in province where we do not have an approved water management plan. So this basically gives guidance, water allocation from rivers and lakes and wetlands, using a sustainable watershed approach, so that we keep water for the ecological need. At the same time, we allow water to use for economic development. Now, in order to do work for the directive, I had to do a lot of applied research to find out information on how much water is actually available in lakes. Now, the information that we needed for the directive is, how much water is available in a lake. So that's the water availability, right? Now, in order to know that, we have to know that, what is the volume of a lake, right? Now, lake volume usually we provide in terms of area capacity curves. So area capacity curves is a set of curves that show you how the volume and surface area of a lake changes with elevation. Now, in order to know or find out that area capacity curves, we actually do need lake bathymetry. So that's one thing. We also need, because in winter time our lakes are frozen sometimes, like the top layer. Now, that means the volume is actually reduced in winter, because a huge portion of the lake water become ice, right? So we also have to find out that what is the volume under ice for that time. Now, if you look at this map, every single dot or shaded area in blue, these are lakes. So we have many lakes in Alberta, but we only have bathymetry data for about 150 lakes. So we cannot use bathymetry data to find out volume or water availability information for all of the lakes, right? So look at the right side of the graph. So it's a sort of conceptual graph that I created. So in the right hand side, or in the x-axis, we have uncertainty in information, and then in y-axis we have data availability. So definitely in an ideal situation where we have, all the lake bathymetry, you actually have very low uncertainty on, estimating water volume, right? And then when you have no information at all, you have a very high uncertainty on estimating, lake water availability. So what we try to do is, we try to develop different models in this range so that, if you have some information, then you can try to minimize the uncertainty. If you have a lot of information, you can also try to minimize the uncertainty as well, a lot. So basically we looked at two different options. One is the analytical, whether we can do some sort of mathematical expression and model the volume of lake water. And then the next approach we looked at is basically, can we develop some sort of regression relationship between information that we know very easily, for example, lake surface area, and can we actually relate that with water volume, and definitely using known lake. So in order to do that, the first thing we looked at is some of the lake shape model that is available in literature. So the first one is we call it Newman model. It's a 1959 paper published. Now I have two different plots here. So the left side of the plot, what I'm showing is the mean depth of a lake and then the ratio of the mean depth to maximum depth. So it's a very important parameter for the lake. Now, as you can see that this is the Newman's model. So Newman's model, it gives you the volume of a lake if you know some parameters like the maximum depth and like the shape of the lake, that kind of thing. Now we try to apply Newman's model and try to develop this kind of plot, and we find out that it has a fixed mean depth to maximum depth ratio, right? Now then what we did, we looked at all the available lake bathymetry data in Alberta, and we tried to estimate numbers for each and every lakes. Now as you can see, our lakes has depth, mean depth to maximum depth ratio like all the way from 0.01 to 0.76. So that means the Newman's model doesn't necessarily work for Alberta lakes, like all of the lakes. Now in the right side I have another plot where I try to plot between, so like the ratio of the volume of a lake divided by the maximum volume of a lake, and also the depth of a lake and maximum depth. So basically for each lake we have a set of points like this. So every set of points is coming out of one of the lakes. Now the far black line is for the Newman's model, and all this set of lines are from different known lakes. So again, you can see that our lakes are way different than the model that proposed by Newman. And then we try to look at the real shapes of Alberta lakes. So we do have some three-dimensional bathymetric information for these lakes. And so these plots are a real thing, but we just change the scale in the vertical axis so that you can actually see the real shape of different lakes. So there are some lakes that has very narrow bottom, like Ethel Lake, right? And then there are some lakes which has very wide bottom, like Gull Lake. So we find out that our lakes are also different. So not all the lakes are a similar geometric shape. Looking at different shapes of different lakes, then what we propose that why don't we look at all the variation of lake shape, like we start from inverse parabolic and we go all the way to like flat bottom, like cylindrical shape, and we try to approximate lake volume as a state them by sort of equation, and we try to vary the exponent to see that how it looks like for different types of lake shape. And based on that analysis, we find out that a majority of our lakes are either conic or parabolic. And again, this is based on about 80 lakes, so it's not representing all the lakes, right? But that's the data that we have handy at the time. So also there are some lakes are pseudo-parabolic, which is in between parabolic and cylindrical, and then we also do have some lakes which is inverse parabolic. So based on all of our analysis, and I do have a journal paper on this thing, but what we find out that we can actually estimate lake volume with some information, and what we need M, and M is a sort of ratio of maximum depth by mean depth, and we find out that number, that parameter actually varies with different shapes from 5 all the way to 1. So if you have information on maximum depth of a lake, if you have information on maximum surface area of a lake, and if you know the lake shape, or if you assume a lake shape, you can actually estimate maximum volume using this formula. And we can change the formula a little bit to actually estimate 5% under ice volume of the same lake, right? So you need to know the thickness of the ice for in order to estimate that number. Now then we thought, because not for all the lake you actually do have information on lake shape, or you don't have information on maximum depth, right? So how do you estimate volume for those lakes? So, and in order to do that, what we have done is basically, we try to find out, is there any relationship exists between lake surface area and lake volume, right? So because lake surface area you can easily estimate from Google Earth or from satellite image, which is readily available to everyone. So if we can at least develop some sort of relationship between lake surface area and lake volume, it would be easier for those lakes where we have no information at all to estimate some sort of volume information for those lakes. So in order to do that, the left hand side of the plot, you can see, we try to plot all of the lakes that we have data, and you can see that we use different legends to show that we have taken samples from different natural regions so that it covers. And interestingly, there's a very good so this is log plot. So we have x-axis, we have log of maximum surface area, we have y-axis log of maximum volume, and as you can see, it's a very linear relationship when you plot them in a log scale. We have the similar trends or similar sort of relationship between the 5% under ice volume and also the maximum surface area. And then again, we try to apply this whole thing for our study lakes, which is 77, and this map is just showing you where all those lakes are located. And you can see that we try to take samples from all the river basins and also all the natural regions here. And basically this plot is showing a combination of everything. So I showed you the analytic equation of maximum volume, right? And I also showed you the regression relationship. Now I have here like 3 different plots here. So definitely the farm black line is one-to-one relationship between maximum actual volume and model volume, right? So what we have done in this plot is we for all those known lakes, we do have information on the maximum volume, right, from the bathymetry data, and then we apply different models to estimate the modeled volume for those lakes. And if you know the lake shape, and if you do have the information on maximum depth and maximum surface area, you can apply those equations to actually estimate lake volume, and those things are shown by these blue dots, right? And if you look at the statistics, when a little bit about the lake, the lake shape, the maximum depth and surface area, you see the R-square is pretty good, and also the percent bias is very, very low. Now for some lakes you don't know the lake shape, because in order to know the lake shape you may need lake bathymetry, which is again not always available. So but you can actually assume that the lake is parabolic, because that's the majority of the lake is parabolic, about 48%. So if you assume that your lake is parabolic shape, then you can actually minimize one of those parameters, which is M, right? And then you actually estimate lake volume, and those things are shown by triangular points. Now you are now applying a little bit of uncertainty, so that's why you see your percent bias is a little bit more than what it was before. And then the last option is again the linear regression that I showed just in the previous slide. So this is where where you have no information at all, you only have surface area of a lake, so you apply those equations to estimate volume, and those things are shown by these cross points, right? And as you can see, because now you are only relying on one information, so definitely your uncertainty is quite higher, so you have a very high percent bias. But at least you have something to estimate when you have no other information is available. We have the similar results for under ice volume, again, which is very important when we allow water for withdrawal in winter time. So this is a very important parameter that we also have to look at. Now, if I come back to the very first like schematic diagram I showed as sort of relationship between data availability and uncertainty. So this is where you should not use any of this model where you have where you have lake bathymetry available. So you should not use any model at all. When you do have some information available, you may use this thing. So for example, if you have information on lake shape and maximum depth and maximum area, you should use those analytic approach that we showed. And when you don't have lake shape information, you can actually assume that a lake is a parabolic, then you can kind of increase the uncertainty, but at the same time we don't have that much data available. Now when you have no options or no data is available, you can definitely get this information, the maximum surface area, from satellite image or any other photos or Google Earth even, and then you can actually apply the regression approach to estimate a volume. Now everything that I talked about, it's being published in this journal paper, so you can follow this link to go and download the paper and read it if you wanted to know more about this study. Okay, so the next thing I want to give you an example of flow naturalization of Peace River. Now the reason I choose this project because I talked about the regulation and regulated rivers, and when a river is being regulated, the natural hydrograph actually change, right? So for example, if there is a dam upstream, it try to store water in summer times and springtime, so you'd see that there is a decrease in flow in summer downstream of the dam, and at the same time, because if some dams they have hydroelectric power, they actually try to generate powers in winter as well, so you'd see there's increasing in winter and fall flow. Now let's start with what is a flow naturalization. So I think as you can see from this slide, this is an example of Peace River. At Peace River, so it's a station in Alberta. So now you see that the hydrograph from 1966 until 68, so this is the natural hydrograph. Now in 1968 in BC, WAC Bennett Dam was constructed. So, and when you constructed a dam, you start filling the reservoir. So you could see there's a filling period from 1968 all the way to late 71, and you see that at this time the flow decreased significantly, right? So this is what happens when you start withdrawing water for filling a reservoir. And then after that, this is the regular operations time, but you would notice that the summer flow is much less than what it should be, and also the winter flow and fall flow is higher than what it should be. So naturalization means try to take out those artificial effects using mathematical model. Now this plot, what I'm showing is like the red line. This is basically an estimated natural flow, and blue line is what is the recorded flow. So basically blue line is what you are measuring at Peace River. At Peace River, the red line is basically what we are modeling to know that if there wasn't any hydroelectric dam upstream, the red line would show you the flow. Now, this is the huge river basin. So this is the map of the Peace River watershed area all the way to Peace Point. It's about 293,000 kilometers square. Now, I want to show you a little bit on the flow, regulations. So, the first dam was built again in 1960s, and you can see this is the location of the Bennett Dam. And when they constructed that dam, it actually created a huge reservoir upstream. We call it Williston Lake. And then in 1980s, another dam was constructed. It's called Peace Canyon Dam. It's a run of the river project. So it created not that huge, but a little bit of storage. It's Dinosaur Lake. And recently, they're also constructing another hydroelectric projects, Site C. Now, so there has been a lot of study done for the Peace River flow naturalization under Northern River Basin study, and then John Taggart, Alberta Environmental Parks, he also did study on that, and those are like hydrologic routing, right? And then there's some hydraulic routing has been done, and also there is an effort of having a combination of hydrologic and hydraulic modeling. It's called the Mackenzie River Basin model. It originally completed in 2011, and then there is an update in 2016 as well. Now, the objective of the study was to reconstruct the naturalized flow. So we use the same model to also gap fill some of the recorded data, because sometimes your recorded data can have gap. So we try to model that as well. Now, this is a sort of demonstration of the model. The way it goes, you have two models side by side. One is we call regulated flow. So we basically run the regulated flow from the very upstream portion of the river, and we route it all the way to downstream. And anytime there's a tributary coming, we actually add those information over here. And then whenever you have actually real flow measuring stations, we try to compare that routed flow that coming from the upstream, and we try to compare it with the flow that is being recorded. So the difference is basically the things that is a combination of routing error and also flow that is not being recorded by any tributaries, surface runoff that coming into the river. And we try to apply those things adjustment in the natural flow model. So the natural flow model is very similar to the regulated flow model, but instead of routing the regulated flow in the upstream, we actually route the naturalized flow from the very upstream, and then we try to route that flow all the way to downstream. And anytime we have a sort of adjustment calculated from that model, we actually try to bring that information and add into the naturalized flow model. This is how it looks like in real life. So the platform that I used is we call Whiskey modeling platform. Again, you can see the natural and the regulated river network and all the tributaries that are coming into the system. Now, we need a lot of information to run this model. We need main stem stations, like these triangles are showing the main stem stations. We also need very good tributary information, so like the tributary recording informations. So those are showing by purple squares. Now, because you need to estimate how much flow is coming from a tributary into the main river, and you don't always have tributary monitoring exactly at the mouth. For example, this map showing you this is the entire tributary watershed. However, the Water Supply Canada station is over here, so it basically gives you flow for this portion. So we had to do some sort of adjustment so that you use that information and the watershed area to estimate what would be the tributary inflow into the main river. So this is a sort of listing of how we receive information. So I told you about the upstream naturalized flow. We actually received this information from BC Hydro, and these are a list of different periods that they provide us those information. We use a hydrologic routing. It's called SCR. It's a stream flow simulation and reservoir regulation system. And basically, it need 3 different parameters, to calibrate the model. This is just an example of how we estimate some of those parameters. So, for example, time of travel is one of those. So we try to estimate time of travel with different flows, and we try to plot a graph and estimate how we can relate the time of travel with flow. So I think I explained it a little bit before, but again, the first thing you would do is you route the flow from upstream node, you compare it with the recorded flow, and the difference we call it local inflows. And then we actually adjust the naturalized flow with that local inflow. So QNat in, again, this is the routed naturalized flow. You adjust that with that local flow to estimate the naturalized flow. Now, when you do that, because sometimes this Q local, which is a difference between routed in and recorded flow, sometimes a lot of routing errors can make this Q local very wiggly. So we actually applied a sort of filter or smoothing algorithm to smooth some of those local inflow. And this is just an example of so blue lines are basically those Q local when you do not apply any filter, and maroon line is the same thing when you actually do apply some of those filters. So it's really helped to smooth some of those local inflows. And then also what happened often, when you run this model, often you ended up with negative naturalized flow, again because of some of this adjustment that we made. So we actually had to develop some sort of algorithm to handle some of those negative inflows. So now, even after doing everything, sometimes you ended up with, very irregularity in, especially in winter times where you have low flow, things could be different, right? So now I have 2 different plot here. So the red lines is basically showing if you do not use any sort of, algorithm to smooth some of those flows, this is how it looks like. And if we apply a sort of 7 days, moving average, it looks like this blue line. However, we did not run those 7 days moving average algorithm in high flows because it can actually dampen some of those peak flows and even shift them a little bit. So we only applied those things for low flow seasons. Now, this is showing again, Peace River above Pine River. So that's the station, and what it's showing is although we have only recorded data from around 1979, basically we actually had able to replicate, or we actually able to estimate some of those historical flow as well using this model. So this is again recorded flow. So, and also there's sometimes you have gaps in recorded flow, so the model can also fill some of those information. So you ended up having a gap-free daily flow data from 1960 all the way to 2016. This plot I'm showing again the naturalized versus recorded flow. So again, the blue lines, you can see all of those recorded flow, right? And then the red lines is showing the modeled naturalized flow for the same time. So we have from January 1, 1969, we have recorded and modeled naturalized flow data all the way to 2016. This is just to demonstrate that how upstream regulation can change the hydrology. So the left hand side I'm showing you a plot for naturalized flow. This different lines is showing the Peace River flow at different locations. Hudson Hope, this is in British Columbia, just downstream of all the reservoirs and dams, and Peace Point is the last station inside the model domain. So you could see that how things would have been if the flow is natural, and this is how it looks like under the regulated conditions. The last example I want to provide is development of a hydrologic model to estimate delta water, and I'm going to explain delta water in a moment. So I want to explain this thing by two different scenarios. So think about a big chunk of land where we have agricultural land, and then grassland, probably some water, and maybe there's some development land like roads or maybe, small paved area. Now, if we wanted to develop this whole land and make it as a sort of urban development or industrial development or commercial development, probably a lot of those grassland or agricultural land will be gone, right? And then definitely the amount of developed land will be increased because you are now paving the land by roads or house or industrial buildings. At the same time, it will create maybe there will be a sort of stormwater pond, so maybe there is a chance to that the water area will also be increased. However, if precipitation falls on left side, what happened, most portion of that precipitation actually lost into atmosphere because of the evapotranspiration, and then some of that will go deeper into groundwater, and a very small portion of that precipitation actually converted into surface runoff. Now look at the right side. Now, because now you are paving a lot of those area by roads or roof or parking lot, things like that, and what happened, when the same precipitation fall on the right side, now there's a big portion of that precipitation actually converted into surface runoff because your evaporation or evapotranspiration becomes much less than what it was before when it was natural. So if you can estimate that the available water in a post-development scenario and in a pre-development scenario, usually the difference is the delta water. So that's what we actually try to estimate here. Now, again, this is sort of in a mathematical way to explain the thing that I explained before. So what I'm showing here, if you know the mean annual precipitation and if you know area of any of those portion of the land, and if you know the mean runoff coefficient, which is basically how much portion of that precipitation actually converted into runoff, then you can actually use how things are being changed from pre to post. You can actually estimate how much things are changing from each portion of the land, right? But at the same time, you also have to consider that the evaporation from water body is much higher than evapotranspiration from a land. So we also have to be mindful that we need to estimate the lake evaporation for that area, and because in Alberta most of the time the precipitation is much less than the lake evaporation, so you may end up with a negative number over here, and you also need how much the water area is being changed, so you need to consider that as well. But this formula will give you a sort of delta water. Now I must say that the runoff coefficient, estimating that number is not an easy task. So what we came up with this project is, we ran a hydrologic model for like about 62 years using daily climate data, and we try to estimate runoff from each and every of those different types of land, right? So different types of land, we apply the model to estimate runoff from that land based on the precipitation that falling on that land. And we try to estimate this number in a long-term average basis, so that the number that you are using is a long-term average number. Now, in order to estimate the runoff, we use SCS Curve Number method. This is a very popular method developed by United States Department of Agriculture. We also have a basic Snowmel runoff model. The model need data in a gridded scale. So the model is developed in a township grid scale. So we needed data, climate data, soil data, and other information in a climate in a township grid. So we have used Alberta Agriculture and Forestry ACIS, which is Alberta Climate Information Services. So they do provide grid-based and township grid-based daily climate data from 1961 all the way to 2016. And so we do have precipitation and then temperature, relative humidity and solar radiation, and all this information necessary to run the model. We also use Alberta Biodiversity Monitoring Institute land cover data, because we do need land cover information, and they do have these different types of land cover classes. And next, we also needed soil information, and we needed soil information in a way so that we can apply the SCS Curve Number method, and for that method we actually need a hydrologic soil group. So we used harmonized world soil data and developed some algorithms so that we can convert that data into a hydrologic soil group. And then we need surface runoff information to calibrate the model. Now again, because the model is a long-term average model, so we had to find out the source of long-term average information in terms of surface runoff. So we do have two sources here. So the first one in the left, you can see University of Lethbridge runoff layer. So this is developed by University of Lethbridge, and they used 30 years of information to come up with this distribution of surface runoff in different portion of the province. And the second layer is came from federal government, is the Agriculture and Agri-Food Canada. It's median runoff, so that's not exactly same as mean runoff, but they're very close. So we use this both layer in our calibration techniques. So this is a sort of complex diagram showing that how the model actually handle everything. So you at the top we have all the necessary information that you needed to run the model. As I mentioned that we do need evapotranspiration data, so we use Morton's evapotranspiration model that was built into this hydrologic model. So for any township it would automatically estimate evaporation and evapotranspiration for that specific township. And then we do have all the runoff models, Snowmel runoff, accumulation, and also all the calibration verification is also built into this system. Now, how the model works. So for example, this is a township, and this is a project area. And we need to find out that if this area is developed in a way, how much extra storm water runoff it would create, right? So that's what I need to know. Now, the first portion of the model is it tried to do a hydrologic model in this township. So it would run the hydrologic model based on all of this information in a township grid, and then it would basically try to compare these three things and try to make them close to each other using calibration techniques. One of them is long-term precipitation minus evapotranspiration. So that's basically very close to surface runoff. The inflow of water, outgoing water, so the long-term average of this number is close to surface runoff. And then we try to match that number with observed runoff, which I showed in those two different layers. And then we also try to match that number with the modeled surface runoff using the surface SCS Curve Number method. Now, when you do this calibration in a sort of township grid scale, you would be able to actually apply those numbers to find out what would be the available water in a pre-development scenario from that small land. And then when you have more information on that small land, you actually provide those information into the model and actually create another estimation of available water for the post-development, and the difference is the delta water. So we applied the model for 3 different case studies where we have all the information, and the results was pretty good. And then we also tested the model for different portion of the province. This is the paper that I mentioned. So it's published last year in a conference. So if you need these publications, let me know and I can share. But this paper will give you more information on how the model works, and what are the assumptions that we have used. So again, this was meant to be a sort of in-person presentation, and because of the current situation, I had to make this as a sort of online presentation. So I know that you are not having the opportunity to ask me questions, but if you have any questions, any comments, please do send me an email, and I'd be happy to help or provide more information on this. Thank you very much.